Okay, guys. Good morning, everyone, and welcome to the new thermodynamics course. This is the new course for the course for the new program in chemical engineering. So some of you are doing this course as part of the second year level in chemical, and some of you as part of the third year. And so really there are different options that I could have taken. To divide, for example, assignments and questions, some for second year, some for third year. But the reality is that it could be too complicated, especially because there is a large cohort. And so what I'm going to do, the topic is going to be reduced to second year level, but everyone will do exactly the same assignments, same course, same everything. I have been asked about the WAMs. You should realize that if you are doing this course as second year, for your WAMs will count as second year course. But if you are doing it as third year, it will count as third year course. And so you don't have to worry because internally the administrative protocols have been already in charge of that. And so although officially the course is 2325 and not 3320, the reality is that behind the scenes, some of you will appear as 2325 and the ones that are third year as 3320. Next year, if there is anyone that hasn't done the 3320, I'm not sure. I cannot speak about next year. But for this year, you should not be worried about which level you are being taught or which level is going to count towards your WAMs. Because as I said, second years will go to second year, third years will go to third year. That is the first aspect. The second aspect, this is very important for the exchange students. Don't book your return home so fast because the exam period is about 4 weeks after week 12. Therefore, if you have booked your trip back, the university will not accept that as a special consideration. Special considerations are only half circumstances. It means if you come to us and say, okay, I have to go back to the United States because whatever, I have already booked my plane ticket, I need the exam in a different date, that the university will not accept that. And so I really warn you, don't try to do that because every year we have exactly the same problems. In week 6, the student said, oh, the exam is in that date and I have booked my return home on this other date. Please bear in mind that it will not be able to request, or you can request it, but it will not be accepted, the special consideration. Following aspect, for those of you, and I should have started with this one, for those of you that they don't know me, my name is Roberto. I'm the course coordinator, and therefore the responsibility of the administration about this course falls on me. It means if there are specific technical questions, for this, my part of the course are mine. For the part of the course of Professor Galvin, will be Professor Galvin, although we are going to talk about that now. However, if there is anything administrative or any problems in general with the course, you need to come to me. So the other lecturers will only be in charge of teaching and evaluation. And if there is anything regarding their part of the course, it's them. If it is regarding the part of my part of the course, is me. If it is something general about the course, it's me. And so if you have any problems, clashes or anything like that, come to see me, the sooner the better. Saying that, the second person to teach this course is normally laureate Professor Galvin, but due to special circumstances, this year will not be able to teach it, and so it's going to be Dr. Van Netten. Dr. Van Netten, she's a research fellow, and she was one of our old best students in the degree in chemical engineering. She's extremely good at public speeches, and she has won quite a few prizes on doing that, and so she will be teaching you for about 3 weeks. The rest of the course will be me. This is an exception because normally 6 weeks I teach 6 weeks, Professor Calvin teaches 6 weeks. As I said, Professor Calvin is not going to be able to teach it, and although it's on the course outline, the second part of the course will be taught by Dr. Kim van Netten. Saying that, let's go to see a little bit about the structure of the course. The structure of the course has 4 assignments. The assignments are submitted hard copy via EB Box. Does everyone knows where is the EB Box? Exchange students, probably you don't know. EB Box is on the other side of campus. Do you know where is the chemical engineering lab yet? The chemical engineering computer room. There is a chemical engineering computer room. At the bottom of the stairs, there is a box. That box, you need to stamp the assignment and submit it. Everyone has the responsibility of keeping a copy of their assignment. It means you submit a hard copy, please photocopy the assignment before submitting it. And the reason for that is very simple. Exceptionally, and to be honest, I never come across a case with full proof that an assignment has been lost, because unfortunately, when assignments have been lost, they are always miraculously related to students with very low performance. And so I never seen an assignment that is lost. However, in case that any assignment could be lost, and for example, I come to you and said, sorry, you don't have the assignment, and I'm not going to do that, it will be discovered by the marks. Said, oh, yeah, I submitted. I will ask you, okay, in half an hour, could you please bring me, or 2 days, could you bring me the photocopy of your assignment? And so I will mark it. But if you haven't kept a copy, that will be a failure. I will fail the assignment. I will not give you an extra week to do the assignment. And so you should keep a copy, a hard copy of the assignments. Always. 4 assignments and a mid-semester quiz. The mid-semester quiz, I want to remember, is in week 7 or 8 from the top of my head. That week we will have only the quiz. It will not be any teaching or anything else, because I imagine that no one after a quiz is ready or have the mood to attend lectures. Okay? And so I will not do that. That mid-semester quiz is a closed book and has a multiple choice questions where we look at how good you are understanding the concepts. And that is normally the part of the course where everyone gets the lowest marks in the multiple choice questions. Saying that, in the last few years, has been relatively a very nice, narrow Gaussian, around 50%, which is not bad. The multiple choice questions, surprisingly, there are 20 questions with 4 options in which you have just to tick. And from year to year, there is always 1 or 2 students that they have only 1 out of 20 right, which is against all statistical odds. Because theoretically, if you give it to a person taken randomly, you should get 25% because you have 4 possible answers. It's very normal we have a couple of students always with 1 answer right or 2. That is something I haven't managed to explain. I have explained thermodynamics, but I cannot explain that from statistics. I don't know. And this, it might look funny, but it's very depressing. Because when you see that a person is paying huge fees, how much are the fees per course?
Like 1,300.
1,300? 1,300. And you cannot even randomly get 25% of a course. Wow, you must have plenty of money for putting 1,300 in the rubbish. More things. The worst part of this course is that we have 4 hours in a row. And believe me, that is nothing related to me. I have tried to change to get a decent timetable with 2 hours block, like was every single year, and this university has changed the timetable. And we have an option of having 3 hours now during the day and 1 hour at 7 o'clock. And I say, no, because at 7 o'clock, who wants to be here? Saying that, and given that this is going to be a year of transitions, most of the lectures will be around 3 hours. Okay? And so what I will do, in most cases, I will do some sort of breaks. And now I will need your opinion. What do you prefer? I will do some sort of breaks with 2 options. We can do breaks of 15 minutes. I go ahead and to finish early. Or we can do a break of 1 hour. You have time to go for lunch. And we continue, and so we are here 11 to 3. What does it sound more appealing? A long break of 1 hour or short breaks of 15 minutes and we finish earlier? Okay, who wants short breaks and finishing earlier? Okay. I think democracy has won again. Good. Just for the record, who prefer long break and finish later? Those two have voted twice, I think. No? Okay, 4. I'm afraid, I think we will probably, most of the times, I will try to do short breaks and finish earlier. So I will try to aim to finish something like 2 o'clock or around. Okay? And so it will be more 11 to 2. Today, the lecture will be exceptionally short. I'm sure that you are going to be extremely sad about that news. And so, because as I said, I'm restructuring the course. And so, this year, for first time, we are going to have a proper introduction to thermodynamics. Has any of you seen any thermodynamics before? Could you please put the hands up? And so all of you knows how many thermodynamics laws are there? Good. Everyone agree, no? Everyone is wrong. There are 4. There are 4. And so one thing I'm going to do this year, I'm going to try to make thermodynamics more than just numbers. I'm going to try to make I will try my best to give you the concept, the understanding of what really thermodynamics is. I will try to make you think by yourself beyond numbers, to try to see the logic of the processes. And that is very difficult. It's very difficult from my side and from your side, because the most common ways of educational system is trying to teach you to give you a recipe to know how to fill the exam and to get a final mark of pass. I'm going to try to make you to see that thermodynamics is there for one reason, that is probably one of the most important courses for chemical engineers. And for chemical engineers, the important courses are thermo, energy transfer, and kinetics. These 3 are really the pillars of your fundamentals towards being a chemical engineer. In fact, if you really realize, and I will explain that today, kinetics and energy are really branches of thermodynamics. Thermodynamics is the fundamental, and from there, depending on the point of view that you use or what you are studying, you get energy transfer and you get kinetics. And so I will try to provide you a very, very big picture of the course. So you need to be a little bit patient, because I will be sending the course notes always towards the day before the actual lecture, so you could have it there in front of you. I will also provide in advance tutorials, except in 1 week, that towards week 9, where I do a hands-on tutorial. I initiated that last year, and the students really like it in thermodynamics, is for doing heat engines. And so everyone really enjoys with this aspect. Following that, books. We have, I haven't brought them the course outlines, but if you look at the course outline, there are basically two books that they are referred to. One is by Moran and Shapiro, Principles of Engineering Thermodynamics, and the other is Smith-Van-Ness, that is Chemical Engineering Thermodynamics. Saying that, basically any book of thermodynamics, if you see them, they practically have exactly the same content. It's very strange that you get a thermodynamics book that is extremely different or has a different structure from the others. And so if you go to the library and want to get one of them, and you don't have it, have a go to any other, because it's for sure will be really, really similar. And the reason for that is very simple. Thermodynamics started to be developed around the 17th century with the work of Otto, Carnot, and many of the, like I always like to make the joke, French Revolution scientists, the ones that they lose their heads during that time. They developed plenty of thermodynamics. Thermodynamics at your level is very well set. Everything is very well known and very well understood. The thermodynamics that is being made in research nowadays goes more towards chemistry or chemical thermodynamics, chemical reactions and processes, that tends to go towards kinetics. So what is the actual fundamentals of thermodynamics have been there for a long, long time. And so it should not be very difficult. There are not many difficult concepts in this course. This course is far easier than partial differential equations for those of you that have done partial differential equations with me. And it should not be the problem. Saying that, there is a little circumstances or a subtle point. It is that the fundamental laws of thermodynamics are with us the whole year. It means when we have the mid-semester quiz, I will examine you of the fundamental laws of thermodynamics, humidification, chemical thermodynamics, and vapor-liquid equilibrium. The vapor-liquid equilibrium and humidification does not form part of the final exam. It means when you do the mid-semester quiz, there is part of the material that is removed from the course, and I will not ask you about that in the final exam, which is a massive advantage. Last year, all the students were really happy with that because you could get rid of part of the material. However, first and second law, they are with us the whole time, and concepts such as work and so on. I would really like this year, for first time, although I know that you have a course on energy transfer, I would like to add a few slides about energy transfer, and some aspects, such as I was commented before, of more modern topics, that although it might not be directly chemical engineering, will be some engineering. And I was asking that before. Do you know what is the lowest temperature achieved by mankind, more or less? Something like that. It's very, very small. Do you know how they do it? They get magnetic fields. It's called magnetic refrigeration. You extract heat from the molecules by alternating magnetic fields. And so, I'm not sure, would you like that from time to time I speak a little bit about these sort of topics or not?
Yes. Yeah.
Because maybe this year, if I talk about them, I might not consider them for the exam, and I will be very explicit with that. However, it could give you a little bit more of enthusiasm towards the topic. Because one thing that is very clear is when you go to industry, you might be a chemical engineer, but you are going to be working with mechanicals, electricals, with all sorts of engineers. It means the more you understand the background of the others or some of the basic concepts, the better it's going to be for you. And so, okay, anything else? Anything you would like to ask me apart from my bank account number? Sorry? Some? These are the cheeky group that is up that sitting, that I got them previously. Ecosystem. I'm not sure if this ecosystem really works or anything. I will try to shout and all these things, but echo doesn't work properly. Do you think that I'm wrong? And so, saying that, as I said, the materials, the slides are there for giving you a guide. But you should really try to make use of the books. Go when you have something that you don't understand, you could try to give it a go in a book, read a page or 2 pages. The books that we recommend are really good. They are really, really good for learning thermodynamics. And so don't hesitate to go through them if you need anything. Any questions, really? Seriously, any questions? Okay. When is the first barbecue of Nuches? Okay, or there are no more Nuches. Okay. Saying that, let's go for the follow good news of the day. I don't think I will take more than 45 minutes or 1 hour in the first lesson. But this first lesson doesn't have any deep concepts, but I have created to try to give you an idea of what really thermodynamics is. By the way, something very important. This Copyright Act means that these course notes and any course note are copyrighted to the University of Newcastle. I discovered last year that someone has put the thermodynamics notes on a server of one of these companies that is charging students for those course notes, which is also a nonsense when we provide always the course note. You are breaching serious copyright law, and I have opened an investigation through the university to see which one was the student that has provided those course notes to a server for making money. But my advice is that copyright, you have the course notes, you can use it. Why the heck do you want to provide, why do you want to make money from that, from your own colleagues? And so, okay. Let's go to the first question. What do you think that thermodynamics does? Or study? What do you think that thermodynamics study? Transfer of heat. And that, they are just probably looking at my slides, or no. That, the origin of the word thermodynamics, although Wikipedia says that dynamics means something that does not change, really thermodynamics means literally changes related to temperature. And in fact, thermodynamics was designed with the objective of trying to understand the working of heat engines. Heat engines are mainly what inspired most of the development of thermodynamics. Many of you think that heat engines are not chemical engineering, but the working procedure of a small heat engine in a car or the ones of the Eraring power station are very similar. And so I will try to take you from the little ones, from the little engines to the large engines with many topics related, including things such as the supersonic planes that they can go to Mach about five times the speed of sound. And so I will try to make you to see that there are very important achievements in engineering, in chemical engineering, related to thermodynamics. And thermodynamics is traditionally divided into 2 areas, the thermodynamics of equilibrium and non-equilibrium. Something in equilibrium, most of you might think that if I do this, this is at equilibrium. But you are merely familiar with equilibrium in mechanics, physical equilibrium in which a body can pivot or can spin or fall down, or the Pisa Tower doesn't fall because the gravity center, the perpendicular, is within the base of the Pisa Tower. However, the concept of equilibrium is far deeper in the aspect of thermodynamics. So the thermodynamics of equilibrium that studies the system from a macroscopic point of view is really the object of our study here. And that is what is called classical thermodynamics. Later on, what we have is a different thermodynamic, microscopic thermodynamics. Is any of you doing chemistry at the same time as chemical engineering? Only 3 guys. Have you studied already? I believe that is Scott who explains statistical thermodynamics. Have you done that course? Not yet, no? Statistical thermodynamics is basically, you got a statistic basis, you start to analyze the molecules of a gas from a statistical point of view, and what you get at the end is the classical thermodynamics. It means we can study the process associated to heat from 2 points of view. Macroscopic, we get something we measure, or let's go to do an analysis, a microscopic analysis, and let's go to derive from here, from this microscopic analysis, we can derive the concept of temperature, pressure, and so on, and all the thermodynamics potential. Non-equilibrium. There are 2 aspects. One is thermodynamics of irreversible processes. Exceptionally, we will see some irreversible processes on this course, but very few of them. Why? Because at the end of the day, from an engineering point of view, if you are having a system that is not at equilibrium, the only thing you have to do in most cases is to wait until it reaches the equilibrium, and you do your calculation. You want to operate a power plant at equilibrium when it has got a steady state. You don't want to see normally so much what is happening if half of the fluid is reaching the turbine, the right-hand side of the turbine, and the other half is not. Because in those cases, really you have to wait about 2 seconds more, and so all the fluid goes through the turbine. So we are not very much interested in thermodynamics of irreversible processes. However, we need to bear in mind that all real processes are irreversible. Finally, non-equilibrium microscopic kinetic theory. And let me put an example. You have really a chemical reaction. That chemical reaction is you start to get an inflow of reactants, and that you have an inflow and an outflow. And now you have to design a CSTR vessel, a continuous stir tank reactor. You need to understand the kinetics, and that is what we are going to see in 3rd year with Professor Yu. Kinetic theory. But at the end, kinetic theory is just basically a part of what is thermodynamics. This is my memory aid. Let's go to understand a little bit more about the differences that I said before about macroscopic and microscopic approaches. The macroscopic approaches has massive advantages. We use parameters of variables to describe the system, the whole system. You speak about the volume of this room, the temperature of this room, the pressure of this room. You will never start to consider that the pressure maybe on the left-hand side is slightly less than on the right-hand side or vice versa. Imagine, for example, we are introducing fluid here, If we are interested in fluid here, we might have here an area, a region, where you have really a high pressure because that fluid is compressed in the air. And that air may come at a different temperature than the temperature in this room. And if that is the case, that area will be hotter than the left-hand side. We are at the classical thermodynamics, the thermodynamics of the equilibrium, and we are looking at from a macroscopic point of view that this room will have only one pressure and one temperature. Is it going to be important? When you reach this sign, at the end of the degree, you might have to do some calculations, non-equilibrium calculations, but not many. No hypothesis about the structure of matter is needed. I don't care if this air, by the way, does everyone knows what is the proportion of nitrogen in the air? Okay, good. Because I have had many years where they were, okay. I don't really, at this stage, I don't really mind much if we have 70% nitrogen or we have 100% nitrogen. Apart from the difference, I would be suffocated and would be dying here. The point of view is that I'm more interested into the pressure that there is here, the temperature, and the amount of material that there is here inside. We have only 3, 4, 5 variables depending on the system. These variables are really intuitive. All of us, we are familiar with the concepts of pressure, volume, and temperature. And the best, as I said before, you can measure them directly. You put here a couple of devices, a couple of thermometers, and these thermometers and manometers and measure pressure. You can have pressure gauges, whatever you want. Very easy to measure. Microscopic. The microscopic approach. How many of you really like mathematics? Okay, that is a very scary. This is, although it's not new, okay. How can you be in engineering and you don't like mathematics? That, honestly, no one likes mathematics.
We used to.
Sorry?
We
used to. That was before partial differential equation. Okay. If you will ever, and one day, just for fun, and I want you to open your eyes, I want you to have your eyes wide open, I will circulate here a book of statistical mechanics that is microscopic approach. If I would try to teach that, I think probably most of you will be waiting for me outside with a fire to throw me to the fire or something like that. Or I will suffer from the 7th death of Mussolini, Benito Mussolini, that was killed 7 times by the Italians. Something like that would happen, but I will bring the book for you to see what is a mathematical approach to thermodynamics. However, sometimes that allowed us to determine things so important such as temperature. Or for example, that approach, how many of you knows anything about diffraction techniques to look at the structure of matter? None of you. Okay, there are, for example, you can get some sort of X-ray sources, and you might not think that you are too much related to the structure of matter, but that no longer is happening because chemical engineering is into nanotechnology. Nanotechnology has become a part of chemical engineering. And you look at the structure of matter. There is a structural factor there that you plug into equations, microscopic equations, and you get the pressure or equivalent pressure of your system. And so really, there is it's also very relatively well developed with inconvenience that the mathematics gets quickly out of hand. Inconvenience, you need an X, Y, and Z, Vx, Vy, Vz for every molecule. And so if we have here 1 mole, we need the Avogadro number. By the way, I imagine everyone knows what the Avogadro number is, no? Avogadro number, anyone problem with the Avogadro number? No? Good. If we have 1 mole, and this room will have many more moles, would be, for example, probably I would imagine hundreds of moles, we will have 6.023 by 10 to the power of 23 variables. The variables are not intuitive. If you have that, if you have molecules hitting here fast or slow, it's something that we are not used to think about that. And definitely, you cannot get one molecule and measure the positions and the velocities, and that would not enter in quantum mechanics. I hate that. This is the one that they put in the cinema saying, turn off your phone. That is the same music. And so I hope that with that, you start to get clear what is the sort of thermodynamics that we are going to study is the upper one, the macroscopic at equilibrium. Now comes a concept that we are going to use quite a lot through this course, that is the concept of universe. The concept of universe in thermodynamics is not the concept of universe in astronomy. The concept of universe refers to anything that is influencing your system, including your system. So really, it's a region, if you have your system, our system is the region of a space that you want to study. And the surrounding is everything outside your system that may or may not influence your system. Obviously, if both of them constitute the universe, you should realize that whatever is happening to the air in the Western Australia probably is having very little influence here at this stage. And so really, universe means your system, what you are going to study, plus anything outside there that could influence your system. It's very normal to have, like the example I said there, you have just an object, you put that object into water. And the water, maybe you have 1,000 liters. Your object is hot, 50 degrees C. Okay, let's go to look at that. 50 degrees object immersed in water. The water is at 20 degrees. What is the steady state solution to that problem? What is the final solution to this problem? What is the final temperature of the object? 20 degrees. Has the water changed its temperature? Maybe 0.0001 degrees, but nothing else. So for that case, the water plus my object is the whole universe. Saying that, I want you also to be conscious, and this is something related to, indeed, astronomy. When you do models of the universe, you go to get use of the thermodynamics laws to understand how the universe is expanding. But obviously, I'm not going to enter in that. And so, now, what is happening that our system from our surrounding is separated by a boundary. But forget about the idea that that boundary is something physical. That boundary could be something that doesn't even really exist. I might say, okay, I'm here, I'm going to imagine that we have 1 meter, from this wall to the end, there is a boundary here. And I'm going to look at everything that is happening on this side. There is no actual boundary. But from the thermodynamics point of view, that is, this imaginary line, or this imaginary surface, is separating my system from my surrounding. That boundary could be fixed, will not change position or shape. Movable, it can move. If you have, for example, a gas inside a piston, you compress a piston, and so that piston is moving. Adiabatic, very important. Do not allow energy to pass through. That is extremely important. Diathermic, always allows you to keep a constant temperature. Permeable allows material to pass both directions. Impermeable don't allow materials to pass any directions. Depending on the boundaries you have to tackle your equation, your thermodynamic equations in a different way. It means when you start to look into thermodynamics, the first item that you need to understand is what is your system, what is your surrounding, and how the system is separated from the surrounding. That would allow you to start to develop or to start to approach to look for the solution to your problem. And that comes that we are going to have three different types of systems: open system, closed system, and isolated system. The open system can change or exchange heat and matter with the surrounding. The closed system cannot change matter, but can exchange heat. And the isolated is not going to change neither matter nor heat. And this slide is providing the largest separation or the largest division on this course. Because in this course, the first thing we are going to look at are closed systems. It means the first part of the course, we are going to be looking into systems that they cannot exchange matter with the surroundings. And that is what traditionally Professor Galvin was explaining. This year, I'm going to explain part of that, and Dr. Van Etten will explain the rest. Later on, the second part of the course, we will move to open systems. And open systems are what we call control volume. And that are super important for chemical engineers. Because basically, every unit operation in which that is operating in a continuous manner, not in a batch, is basically an open system. That would be the same difference as batch and continuous processing. And so, really, most of the unit operations, pumps, turbines, condensers, evaporators, stereoreactors, most of them are really open systems because you can exchange matter and energy with the surrounding. Sometimes we'll put the limitations that we don't change energy, but in general will be like that. And so that is the main divisions that you are coming across in this course. There is first the fundamental laws of thermodynamics. We'll explain it. We'll explain it always considering that the amount of matter in our system is fixed. Saying that, if you expand your system, you might have matter going from one side to the other. But that is also a control mass system because cannot exchange anything across the boundaries. Do you see that difference? It means you have a boundaries, nothing passes through the boundaries. However, it can pass from one side to another. For example, if you have two gases separated by a boundary, we can have all of them isolated, and when you remove the boundary, gas will go from one side to the other. They will diffuse. And that diffusion, but still kept the amount of material within your system constant. You are not putting anything inside, or you are not removing anything from there. Isolated systems are the easiest one to deal with because the isolated system cannot exchange material or energy. And when I say energy, basically, I'm really speaking about any form of energy, including work. Okay, and so far, we have seen what is thermodynamics, what thermodynamics study, what are we going to focus? We are going to focus on thermodynamics of equilibrium and from a macroscopic point of view, and therefore we are using a small number of variables. And after that, I say that we are going to be looking into two concepts, open system and closed systems. Closed systems will be mainly the first 6 weeks of the course. Open system will be the second 6 weeks. So far, we haven't done really much. Today is going to be just a little bit of setting the fundamentals for starting to look at the concept of work and first law next week. Any questions, guys? Am I going too fast? Hopefully not. I imagine that you must have seen this probably before, but I do think it's a very good option to have a recap. Thermodynamics, variables, and equation of state. The thermodynamics variables are classified normally into two types, extensive and intensive. The extensive depends on mass, volume, number of moles. It means you increase the size of your system, that variable will increase. Volume is the most basic one. If you multiply by 2 the size of your system, you multiply your volume by 2. However, pressure and temperatures, they are not within that group. Pressures and temperature are intensive, because temperature will be a macroscopic property that will define this system. And if I multiply by 2 the size of the system, the temperature may be completely exactly the same. That also gives us something else. Apart from pressure and temperature, the extensive variables can be converted into intensive. Do you know how? We divide either by mass or by number of moles. And so it is normal at this convention, sorry, I should have added here, this convention says that when you have extensive variables, you write capital letter if you can convert them into intensive. And when you divide it by number of moles or by mass in kilograms, you write them with a small case. So all the variables, such as, for example, volume, if you refer to a specific volume, it means volume per number of moles, it will write a small v. But if it is really referring to the actual extensive variable, will be capital V. I don't request any of you to really be very strict with this aspect. However, that is the actual convention that you will find in every book. If you find a capital letter for energies, volumes, or whatever, will refer to an extensive. If you find the same letter in a small case, will be divided by a number of moles or by kilograms. And so be really careful with that, because most of the tables that we are going to use on this year, they are reported, the extensive variables per kilogram. It means appear with a small case. This is a very important thing that I forgot to add. And so please add it for your slides or whatever, because small case normally means that they have divided the variable by moles or by kilograms. And always, for whichever system you have a equation of state. The equation of state is the one that is linking all the variables of your system. And here, we are having the most popular one, that is the ideal gas law. Ideal gas law, as you can imagine, there is no gas that is ideal. And was developed a long time ago, and is really useful. Probably, I'm not sure if I'm going to enter this year too much in that, but you should be very aware of a very important aspect. Ideal gas law is derived for molecules that are very small and very low pressures. It means when you have a gas in which the molecules are relatively large, the ideal gas law doesn't work. And so I might enter a little bit there in future weeks, but at the moment, we'll leave it there. P, V is equal nRT. R is the ideal gas constant. Everyone asks me, Roberto, do I have to memorize this? No, really. Okay, and so it's nice that you know that this 8.314 joule per mole and Kelvin, but memorizing is very normal that you forget, and I'm not going to jeopardize your future with thermodynamics because you are nervous in an exam or mid-semester quiz and you cannot remember the ideal, the ideal gas law, yes, but not the ideal gas constant. Ideal gas constant, you be really careful. There are hundreds of units that you can use. And so I advise you to get always this one. And by the way, if I want to pass this unit to kilojoule per kilomole, what do I have to do? Good, nothing. It means this is the same as kilojoule per kilomole because you multiply by 1,000 numerator and denominator. You have to do nothing. Okay, good. You're making my day happy. This is ideal gas law. We will use most cases, but you should be really aware that when you start to increase temperatures and pressures, this is not a very good approximation. Saying that, we are going to do problems with 2000 degrees C, and we are going to use ideal gas law, but you should be aware that is not going to represent a real substance. Let's go to set now a little bit more of concepts. Thermodynamic transformations. Although, if you realize there is a little bit of, could be a little bit of confusion, we are speaking that we are going to look at states of equilibrium. Have we said that? But saying that, we are going to do hypotheses about how the system changes. Because if your system is always at equilibrium and we cannot change it, basically there is nothing to do here in this course. You have to do calculations. And the calculations are regarding transformations. Although those transformations, there is a way of dealing with them that to make them to look like an equilibrium state. And so, look at the concept that I have there. Degrees of freedom is the number of variables that can be freely changed in any given system. So, if we have, for example, a gas that is here enclosed, this gas is characterized by pressure, volume, and temperature. Normally, we assume that the number of moles we know, and so we have 3 independent variables. However, these 3 independent variables are linked through the equation of a state. And so really, I can only move freely 2. Pressure, volume, volume, temperature, pressure, temperature. And so if I can move freely 2, what is happening here, we can start to move it, and we want to look at a transformation. The degrees of freedom are 2. If now I say, okay, let's go to transform, let's go to make the volume constant. As soon as I make the volume constant, there is only 1 extra variable. With that, what I want to say in short story is that our transformations, in most cases, they will say isochoric or constant volume, isobaric or constant pressure, isothermal constant temperature, or adiabatic, and this PV to the power of gamma is equal constant. We will look at that a bit more. I cannot have 2 of them simultaneously. I cannot have a process that is isochoric and isobaric because I don't have degrees of freedom. I cannot do that double restriction. And so the following aspect is when you are going to look at any transformation, you need to identify, first of all, is that adiabatic, is that isothermal, is that isochoric, or is that isobaric? And you have to know that you can have only one of them. You cannot have more of them. For having more, I would have to release another extra degree of freedom. For example, I could have an isobaric, isochoric, if I'm allowing material to enter or going out from here. And so I can be moving both of them if I'm removing materials or adding it. Otherwise, I cannot have isobaric and isochoric. I cannot have adiabatic and isothermal. And that tends to be very confusing because in most cases, the equation that you have to solve will already tell you this process is isobaric or this process is isochoric. It's very strange that you have the data and you have to find out the final state and to know if it is one or the other. Normally, you will know a priori what sort of process is. Therefore, you should understand what sort of equation you need to use in order to deal with that. As I said, we are going, all this, today there are no tutorials, but next week when I start to look at work, we'll start to do tutorials. And we'll start to do plenty of tutorials. Tutorials that will start from the most basic points. These are the transformation. I know that I have put a little, what do you prefer? More writing or less writing on the slides? Sorry? More or less? Okay, fine, that's fine, no problem. It's because personally, I like more to have less because I just want to look at the key points. When you prepare slides for public presentation, if it is not a teaching, you should never do that. If you go for a job interview and they ask you to do a presentation, never do that. Never. Because it's a presentation, not a lecture. And so, really, the more you are advancing, feel free to ask me things about job interviews and so on, because I know a little bit. And so, for the time being, I like to add more text. We are going to have certain amount of text, but don't fall into the trap. These slides are not sufficient to learn a course. You need to use books. I'm not going to copy and paste a book. The books are there. Please use the books because they are really good and really enjoyable. We have been speaking that we are going to deal with a part of thermodynamics that is the thermodynamics of equilibrium. However, I have not defined equilibrium yet properly. I have spoken about it in a very vague way and speaking about mechanical equilibrium, and I said in thermodynamics the concept of equilibrium is much wider. And it's much wider because we have really three types of equilibrium. Mechanical equilibrium, that is the one that we have learned in physics, no unbalanced forces. It means a system is at equilibrium. If you have a piston and you push that piston at once with a large strength, there is no equilibrium there. A thermal equilibrium, when there are no temperature differences between both sides of the system. And a chemical equilibrium, when there are no chemical reactions proceeding. The chemical reaction has reached a steady state. Yes, it might be having reactants transforming into products, but this at a steady state. And so we need to have really a thermodynamics of equilibrium when we have the three of them. We are going to look at mainly the only cases of non-equilibrium that we are going to see are mainly mechanical and thermal. Mechanical equilibrium when you have cases of pistons expanding against a vacuum. the thermal equilibrium, when you have dissipations, for example, in a turbine, you could have energy dissipations, energy that you cannot recover. And so we are going to look at a little bit about non-equilibrium, not much. Most of the cases will be thermodynamics of equilibrium. And this probably, if I would say that there is a concept that is difficult for you guys, and I'm not sure why, it is the concept of reversibility. Have you seen reversibility before? How many of you have seen the concept of reversibility before? You've never seen it? Okay, good. Reversibility is really a little bit awkward because, like you could see at the bottom of the slide, all real processes are irreversible. So a process is called reversible if you can move backwards the state of your system and the universe to the initial condition. It means you have a transformation, and at the end of that transformation you said, no, I want to go backwards. And you manage somehow, by a device, a machine, you can invent it, whatever, you can go. The state of your system goes backwards. But the state of the universe, it means your surrounding, should go backward. If the state of your system goes backward, but the universe doesn't do it, the process is not reversible. Reversibility involves both system and surrounding. And that is where the main problems or the main confusion comes to you guys. Because you think, okay, I depart from 1 atmosphere or 101 kilopascals, from 101 kilopascal to 98 Kelvin, I hit it to 398, and now I'm coming back to the initial circumstances. Okay, this process is reversible. I come back at the beginning. No, because you might have done something in the universe. And that something is normally energy that you have dissipated without realizing. That poses a really, really problem, because types of irreversibility will be mechanical, like I said before, gas rushing into a vacuum, thermal, friction of electrical resistance, chemical, diffusion of two dissimilar gases. If you look at, for example, the case of chemical, you cannot even return the type of the system. Imagine you have gas A on the left-hand side, gas B on the right-hand side. You let them to mix. Are you able to separate both gases to leave that exactly like it was at the beginning? Very difficult. You can, but it's really difficult. And so all those are the type of irreversibility. As I said, we are going to be looking at a little bit the mechanical, and the thermal is very important in power plants. Because in power plants, when you have a substance passing through a turbine, it's sure that you are going to dissipate energy. You are going to dissipate energy in the pipes. Have you done already safety and risk with me? Okay. When you have a fluid going through a pipe, and that happens in the actual power plant, every certain distance you have to put a pump to pump that fluid again. Why? Because the friction with the wall is dissipating new energy. So you need, every time that you have a dissipation is an irreversibility. You need to put a pump. And so you need to get materials to try to compensate. You can take your system to be like it was before. The fluid can recover the speed, the velocity. But the universe has got part of energy that we are not able to recover. And so irreversibilities are important in power plants because a big amount of energy is dissipated in the turbines, in the condensers, could be in many places. Okay? And so really, we are going to look at them a bit, not much, as I said, And these basically, the calculations are relatively simple, just a percentage or so on. And what is a quasi-static process? A quasi-static process is a process during which the system is at equilibrium. And that, if you realize, I came with that sentence yesterday to explain it. This can only be achieved by changing the state of the system at an infinitely small rate. The name is somehow paradoxical, as nothing in the real world can change infinitely slowly. And so, look at how a quasi-static process works. Let's imagine we have here a piston, and we have a big weight of, I said 10 kilos, good. You put it in the piston. That is going to push the gas at once fast, very fast. But now we are going to start to do it in 2 kilos weights. Push it a little bit more, until you get the final state as at the beginning. We make it now smaller, 1 by 1, kilo by kilo, until we have achieved the same as we achieved there. However, this process has been slow. The limiting case is when these weights are infinitesimally small. Therefore, we need the whole time of the universe to really do that process quasi-static. That doesn't exist. However, we can still imagine, under certain circumstances, that that is the case. And so with that, we minimize the amount of energy that we dissipate and many other things. So practically most of the process we are going to see, we are going to assume that they are quasi-static. And that has an advantage. While you have a system passing from equilibrium to equilibrium, you can use the state of the equation of a state to define the state of your system. However, if the process is abrupt, during the actual transformation, the equation of a state is not valid. It means if you have a piston and you push it, whatever is happening, you cannot use the equation of a state in this process. You can use it for the beginning and you can use it for the end, but you cannot use it for the intermediate aspects, for intermediate process. And so that is the concept of quasi-static. Most of, as I said, 99% of the examples we are going to be quasi-static. Only 1% of them, they will not be quasi-static. And this is going to be only rushing into a vacuum. It's the only case we are going to see that is not quasi-static. Too boring? Hopefully not. I'm shouting and losing my voice like happened normally to me during my first semester. And that we come now to the thermodynamics laws. And like you pointed out before, there are 4. The zero law. If a system A is in thermal equilibrium with a system B, and the system B is in thermal equilibrium with a system C, A is in thermal equilibrium with C. This is extremely simple because A is in thermal equilibrium with B, B is in thermal equilibrium with C. Imagine that for being in thermal equilibrium, A, B, and C are completely isolated from outside. The conclusion is that although C might not be touching A will be in the thermal equilibrium as C. And you can derive from this transitive property, and I'm not doing it because this is engineering, this is not physics. I'm not going to do it. But you can derive from there the concept of temperature. The conclusion to that is that the temperature of A is equal to the temperature of B is equal to the temperature of C, which is something that you can see logically But as I said, it's not worth it even really to spend time with that. First law. First law, as it says there, is an energy balance. I haven't, if you realize, in this first introductory notes, the only equation I have put, I think, is PV equal nRT. I haven't put much. Establish the conservation of energy. I don't know, have you ever heard that energy you cannot create or destroy it, you can only transform it? Have you heard that? No? And it's true. The first law is telling you that you can transform the energy from one place to the other. Energy is always there. Energy is always there. Energy forms part of the molecules, it forms part of the matter. You can disintegrate a material, and that material would release energy. That is the matter, or is the chemical bond. When you have a chemical reaction, some reactions, they produce heat. Why? Because the chemical bond, the energy of the chemical bond, is being transformed into kinetic energy, and the material is getting heat up. And so basically, first law tells you, doesn't matter, you need to have an energy balance. What the first law does not say to you is, can I have any energy balance? And the answer is no. There are things that are not allowed. There are transformations are not allowed. And so the second law of thermodynamics is precisely introducing the concept of entropy. And that concept of entropy is the one that is going to tell you if that energy transformation can be achieved or not. And so if you realize first law associated to temperature, zeroth law with temperature, the first law I haven't said, but is associated to internal energy. The second law is associated to entropy. And so that entropy is telling you something. I like always to put this example. You have a ball. The ball, you can hit the ice with the ball, and so that kinetic energy is going to the ice because maybe it's going to bounce a few times, and so it will go to the ice probably as a little of heat. Mainly. How many of you have seen the opposite? How many of you have seen that the heat of the ice is transferred back to the ball and the ball jumps spontaneously? And you might be thinking, oh, Roberto is completely crazy. Has been taking something last Friday and still has hallucinating, seeing the ball going up. No. It's possible to demonstrate that from the macroscopic point of view that is not possible. However, thermodynamics fluctuations of the heat in the ice do not stop that ball gets that energy and jumps. The probability you see that is something like once in twice or 3 times the age of the universe. It's very small, but so if you see next week the ball doing that, question yourself that is nothing related to entropy, probably is what you have taken the night before, or an hour before, okay? And so entropy determines what can happen and what cannot happen, which takes us to the third law. Have you seen the third law before? In which course have you seen the third law? Or you haven't seen it? In Phys Chem, no? The third law is called Nernst's postulate. Nernst was the scientist that says, he formulated that, but not exactly with these words, said that the origin of entropy and the inaccessibility of the absolute zero. The absolute zero can never be achieved. And the reason for that is nothing related to thermodynamics, it's related to quantum mechanics. Now, that is very important because tell us that at the absolute zero, supposing you could achieve it, the entropy of any system is zero. Which therefore, and now I will warn you the first time, many thermodynamics tables put the entropy zero at 298 Kelvin or 273 Kelvin sometimes. depending. So be careful with that. When we look at thermodynamic tables, I will remind you, some tables, especially if they are from the net, from the internet, they put the 0 at 273 or 298 because you are going to use a difference in entropies, and so it doesn't really matter. The reality is that entropy is 0 at the 0 Kelvin. 0 Kelvin that cannot be accessed ever because you have 0 Kelvin would represent all the molecules completely frozen and stationary in one point. And like you have studied physical-chem, I imagine you have studied the uncertainty principle of Heisenberg that say you cannot have something fixed and knowing its velocity. It means you cannot have something stationary that is not moving. So it's really quantum mechanics which prohibits that. It's nothing related to thermodynamics. Saying that, it's not surprising that every time more is more and more difficult to extract energy from a system to make it, to cool it down, 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 down. Okay, and so we have visited very quickly, as an introductory, the thermodynamic laws. And we are now about the concept of temperature. It is a very interesting. I thought many times about, I have prepared the slides, I don't know how many years to introduce how to define concept of temperature. But the reality is that temperature is very important for you to understand that is related to the kinetic energy of the molecules. The hotter the gas, or the liquid, or the solid, the faster the molecules move. Now, temperature was initially derived empirically without any knowledge or understanding about the heating of the molecules. It was taken a control gas, a constant volume gas thermometer or devices with mercury. They put certain amount of gas and they studied what is the behavior of the mercury rising and going down depending on the amount of gas that you have there. And from there, they derived a parameter that was later known as temperature. It means temperature was derived empirically with no knowledge of what their physical meaning was. We have 4 here scales, thermometric scales. They call it thermometric sometimes, other times temperature scales. We are using mainly the Kelvin and the Celsius. And the Kelvin, the triple point of water. Do you know what is the triple point of water? How many of you knows? Yes. Good. Where the 3 states coincide is 273.16. And in the Celsius scale is 0.01. The Fahrenheit 32.02, Rankine 491.69. The boiling of water, the boiling point of water is 373.13, 99.98, 211.98, and 671.67. I'm sorry, American students, are you used to the international system, or you still see everything in the imperial? You in the international, good. Oh, good. And so, with respect to previous year, Professor Calvin used to like to do questions in British system, in imperial system. I'm removing that from this year. I'm sorry, it's nothing against the imperial system. I don't like it. Basically, I don't like it. If you like it, because I hate to have a GC and the pounds per square inches that unfortunately you come across in many Americans' books. But goodness me, the international system is there. And so I'm going to do everything into the international system, and I'm asking Dr. Van Netten to do exactly the same in the international system. Okay? I don't want anything of the British system. Saying that is the first simplification I introduced in this year in this course. And I hope I know the happiness face. I can see the happiness face when I said I don't like the imperial system. but hopefully that will allow you to focus a bit more on the concept and less into the calculations. You have the conversions here. From time to time, more is merely practice when you get somewhere and tell you your aquarium should be better into 70 and 80 degrees Fahrenheit. And so if you have certain hobbies and enter on Google or whatever, and you get used to the Fahrenheit system, it's very good because a lot of information is there in that system. I really like Celsius and Kelvin. And I remind you something very important. All the thermodynamics equations are prepared to work in Kelvin. And so when they say that, and many people joke, when you reach my part of the exam, and I tell you, if you don't remember how to do anything, if you remember that the equation should be in Kelvin, write it down and I will give you some marks. Because if you go to a power plant and you get the efficiency of the plant and you try to use the simplification with temperature, you put it in degrees C, you are getting a number that doesn't make any sense. And so I do consider that it's pretty important that you remember that temperatures should be in Kelvin. Saying that from time to time we use degree C because equations that depends on difference in temperatures, the difference in temperature is the same in the Kelvin or in the Celsius. And so if it is a difference in temperature, nothing happens. But if you have a ratio or a product with no differences, you have to be careful, consider Kelvin, only Kelvin. I think that the final slide is thermodynamic units, pressures. We will get used to work with the three. Normally, if you realize, if you say to me an atmosphere is a bar, yes, that's fine. Or is 10 kilopascals, 1325, I remember more or less, but it's not an important thing for you to remember exactly 6 significant digits. And so these are the unit of pressure we are going to use. Volume, I haven't put it because it will be mainly cubic meters or sometimes liters. And so I'm not going to do anything excessively strange. Wow, I've been 1 hour. I didn't expect to be an hour talking. And with that, I'm going to finish the first unit of thermodynamics. Okay, and so don't count that it's not going to be so short the following weeks, but it's not going to be 4 hours. Okay, because there are no humans that I can. Your colleague has already been sleeping, eh? I'm telling you, one of the students I have a few years sleeping, she had narcolepsy. And so, if you think that you fall asleep, not just with me, with everyone, go to the doctor and don't leave it. Never. Because your life could depend on that. I started to have a period of falling asleep everywhere, and I finished going to the doctor, and I was having sleep apnea. And so, really, hello, nice to see you.
I just have a question because I think.
Wait.
about that?